Okay, so in chapter 17, which you're still working on, but we're going to start the notes for 18, we did some problems in which we would find the sample proportion, p hat, and say that if certain assumptions are met, we believe that this estimates the population proportion, p. And then we could go on to say that we were pretty sure that the true proportion is within two standard deviations of p hat, right? We're like, yeah, I'm pretty sure. Not absolutely sure, but I'm pretty sure. All right, so if I do a sample and I go two standard deviations to either side, I'm relatively certain that the proportion of the entire population fits somewhere in between those two. And if I want to be even more sure, what I can do is do 3 standard deviations to either side. Right? So today what we're going to do is, instead of saying pretty sure and very sure, we're going to put some numbers to this. We're going to do something that's called a confidence interval and look at the margin of error. Let me go ahead and give you the formula sheets because some of this is on there. So I'm going to take you through the derivation of this. So whenever we estimate the standard deviation of a sampling distribution, we call it the standard error. If you look on the back, that first table, all the way over to the right, notice it says
standard error.
Yeah, standard error of the sample statistic. Okay, and you look at this formula and you're like, wait a minute, isn't this the same formula that we did before? Uh-huh.
Oh, look at that.
It's the same formula, we just didn't call it the standard error. Okay, so they kind of set you up there. They're like, okay, you already know this. This is the standard deviation that we found. This is actually the standard error. Okay, so nothing new there. So critical value, you may or maybe not. Remember that back earlier in the year, we said that about 95% of the values in a normal model fall within 2 standard deviations of the mean, which is what we were just talking about from last night's homework. It's actually just an easy to remember rule of thumb to find that the actual number of standard deviations to capture 95% of the values. We can use inverse normal if you're doing it on a TI calculator. I'll also show you how to do it on the NumWorks in just a second to find that it's actually 1.96 standard deviations to get 95%. It's not quite 2 standard deviations.
Can we just say it's 2, usually?
Well, what you do is you say 2 standard deviations is going to capture 95%.
Okay.
It just captures a little bit extra.
Gotcha.
Okay? So let's do that. Grab your calculator.
I charged this bad boy last week.
You did? I did too. I'm dying. See, look. Oh,
Oh.
the battery. No.
It'll be gone within a few moments.
It already is gone. I'm sorry. I did not come prepared to class. That's on me.
You can use mine, Mr. Davis. Oh,
I'm using that. I'm using this one. All right, so we'll go to distributions.
15.
We want a normal distribution.
Normal.
And let's do this like it was a z-score, right? That's the easiest way to do how many standard deviations. So where the mean is 1 and the mean is 0 and the standard deviation is 1.
The mean is 0. Standard deviation is 1.
All right, that's when you're doing z-scores. And what I'm going to do is I'm going to look if I want to capture 95% of the middle of the data. So I don't want the stuff that's extreme.
Right.
I want the heart of the data.
The heart.
So I'm gonna go over here and go, okay, I want my probability to be 0.95.
Oh my gosh.
It's gonna be about 1.96 standard deviations to either side of the mean.
It's gonna be what? Sorry, say that again.
1.96 standard deviations to either side of the mean.
So that's the margin. Oh wait, no. That's the.
Well, we'll talk. This is the 1.96 is actually called your z critical,
Okay.
or just the critical value. And we denote it with a z and an asterisk. Some people call that z star.
Star.
Z critical is what a lot of times we'll call it, or z crit. So we can find that for anything. So if we wanted to go, okay, well, I keep forgetting to minimize this before I. Well, let's say I only wanted to, capture 90% of the data. Okay. How many standard deviations do I need to use? 1.644, blah, 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 blah. That's how many standard deviations I need to get if it's truly normal to capture 90% of the data.
Oh, cool.
So you can do that for anything.
Very cool. Very cool.
All right, now, remember that a z-score is found by doing what we observed minus the mean over the standard deviation. I swear to you, before the end of the year, I'm going to remember to minimize that every time I use it. So, on our problem, our z-critical score is going to be equal to the observed proportion from our sample minus the proportion from the entire population divided by the standard error p hat minus p is how off from p hat is. We call this the margin of error. So substituting that in, we get that z critical is equal to the margin of error divided by the standard deviation or standard error. Solving for the margin of error and using our formula for the standard error, we get this, that z critical times the square root of p hat q hat over n gives you the margin of error.
So P hat and Q hat are just P and Q, right? Because
Yes, but the p hat and q hat are the observed.
Okay.
Because what we're going to use this for is where we don't know the proportion of the entire population,
Which would be P hat.
The-
Oh no. We
which
don't
would
know.
just be p.
Okay.
P hat is the observed.
Mhm.
P is the proportion of the entire population. So P is a parameter because it's for the whole population. P hat is a statistic because it's taken from a sample. It's not everybody.
Okay.
That would be a formula that, and I'm trying to think, if you go back to the first page, okay, so if you look where it says confidence interval,
Mhm.
and it says confidence interval is equal to the statistic plus or minus that critical value times the standard error, that is the margin of error.
So ME is statistic.
No, ME is the critical value times the standard error. That's your margin of error.
So margin of error is
The margin of error is your critical value, in this case z star, times the standard error.
Okay.
And then what we're going to do is they don't give you all of that at one place, but they talk about the standard error on the back. They tell you how to get that. Right?
Standard error is p hat q hat square root over n.
Yes. Square root of p hat q hat over n.
And then
Z critical is found from, well, how many standard deviations do you want it to, what percentage do you want to be in there? It is the number of standard deviations that you want to use. Which, when you think about it, makes sense.
Yeah.
Z star is, well, how many standard deviations do you need to use? Times, what is the standard deviation? That's going to be your margin of error. So what we do then is, to get a confidence interval, we take our observed proportion minus the margin of error, comma, our observed proportion plus the margin of error. And that gives you this interval where you're like, okay, this is my confidence interval.
So in order to find in order to find the critical value, you have to use the standard error.
No,
Oh.
we just did that on your calculator.
Oh.
Right? If we want to collect 90%, my Z critical is 1.644.
So you don't ever have to do it by hand?
No, you don't have to do that by hand.
Oh, okay.
That finding Z critical is always going to be something you're going to use your calculator for.
Okay.
So the Z crit is always going to be a calculator thing. Finding the margin of error, they may ask you to show that, not even show, but I've seen ones where they have a multiple choice question where they say, which of these will find the margin of error? And they give you basically this with the Z crit, the P, the Q, and the N, all that gives you all this in there.
Oh,
Right.
Like numbers or like that formula?
Not the formula, with numbers.
Oh.
So you're having to go, okay, I do know this formula. Because you can do all this without on a calculator. I'll show you that in a minute. Don't worry. Don't forward think too much.
Oh, will we have this will this be online for us, or can we have a printed copy?
I'm not sure which it's going to be for you guys this year. I would imagine it's part of so you may have to scroll back and forth and stuff. I wish that they didn't. I wish that they just had, here you go. Because having to scroll back and forth is a pain. They may have it bookmarked somehow. I don't know. By the way, did you guys get the email about practice exams?
No.
Okay. I'll forward that along to you guys. If you have a College Board account, you can go in and they have, it's not a full practice exam, but it's like a sample of what your exam is going to look like online. And you can look at any of your exams.
Oh, okay.
All right. So using this, we can get what's called a confidence interval. And you notice, didn't minimize it. Like here, we captured 90% of what's in there. We would call that a 90% confidence interval.
Okay. So those, the negative 1.65
Are the Z crits.
Z-crits, but that's not the confidence interval. Right?
No, we'll get to that.
Oh,
So would they say find 3 standard deviations of it, or they'll say
They'll say a 96% confidence interval or 84% confidence interval. we're getting to that. All right, so what we're doing here is called a one proportion Z interval.
More qualifications.
These qualifications are the same ones we've been using,
Oh, okay, good.
right?
Yeah.
It needs to be random. Needs to be independent, at least as best as we can check, and so we need the 10% condition as part of independence. Independence is, 10% doesn't guarantee independence, but if you don't have it, we can guarantee it's not, we think it's probably not independent. And then the normal assumption, which is the success failure condition, same one we've been doing. Okay, when those conditions are met, we're ready to find a level C confidence interval for the population proportion P. The confidence interval is given by P hat plus or minus Z crit times the standard error of the observed proportion. Okay, that's the formula that's on the front. They just give it to you in words instead of giving it to you exactly like that. And the reason why they give it to you in words is because it actually works for like 6 different things. But it's always the same basic idea. You have, what is your statistic? What did we find? Well, we found the proportion of green M&Ms was 18%. So we think that's the actual proportion of the entire population. And then we would do Z star. We would go, okay, how we have to figure out, given whatever the percentage is, how confident do we want to be, times the standard error of our observation.
So where does the margin of error come into play?
The margin of error is all of this.
That whole thing is margin of error.
That's margin of error.
Oh, and that's why at the bottom it said plus or minus margin error. Okay.
Correct.
Same thing. Okay.
Right. And so on your sheet, on your pink sheet, it gives you this formula, but it gives you this formula in general.
So the star,
Z star, yep,
yeah, for that one, let's say if it was 95%, then it'd be 1.96.
9.6. Yes.
Okay.
Yeah. All right. Where the standard error is this standard error formula that we've been doing. And you notice on the back, there's if you look under that column with standard error, it depends on what you're doing. What we're doing is one proportion. And right underneath that, they give you the standard error formula, right? There's also one for 2 proportions. There's also one for means. There's all these different ones.
And we'll learn how to do them all.
Yeah, but they're all basically the same idea. All right, couple things to notice. As n increases, the standard error decreases, but not at the same rate. So if we want to decrease our standard error by a factor of 3, we would need to increase our sample by 3 squared, which is 9.
Because of square root.
Because of the square root. Right?
Oh, yeah.
Also notice that as the confidence level increases, the margin of error increases also, making our confidence interval wider. So to be more confident, we need to be less precise. This is what I always remember. If you want to be really confident, you need to be less precise. If you want to be really precise, be prepared to be less confident. Okay, and I think that's you kind of wrap your head around that and you're like, oh, okay. If I'm trying to predict the score in a game, if I give you the exact score and I say, I think that the Texans next weekend will score exactly 13 points. How confident am I of that? Not very. If I say they're going to score between 0 and 78 points, I can be really confident that they're going to be in that. So, the less precise, the more confident you are. The more confident you are, less precise.
Do you always want to be more confident rather than precise? Or does
Well, that's the question.
Oh,
There's always a tension between those two things. Being more confident but being less precise, or being more precise but less confident. All right, so what does 95% confidence means? So we took a sample, and like the one from last night's homework where they got that it was 18% green M&Ms, right? If we do a 95% confidence interval, what we're going to do is we're going to look at what we got, the 18%, plus or minus our z-crit times our standard error, and we're going to go, okay, I have this interval now. I think that 95% of the time, a sample of this size will produce a confidence interval that will capture the true proportion. Not all of them will, but I think that 95% of the time it will. Okay? So the proportions we find are going to vary from sample to sample. You might get 18% one time. You might get 17.1% one time. You're going to get different proportions every time. Right? The true proportion does not change. The proportion of our entire population doesn't change. What changes is the proportion in our sample. Our sample proportion is going to vary some. Remember, we called that sampling error, right?
So sampling error is the
It's unavoidable.
yeah, because we're never, unless we use the whole population, we're never gonna find.
Exactly. When you take a sample,
It's always gonna have some sort of error.
you could hit it exactly,
Well, that's like
but when you take several samples, they're going to differ from each other.
okay.
So the theoretical mean is the actual population, right?
So we're not talking about means here. We're talking about proportions.
Okay,
The theoretical, what now?
mean.
We're not talking about means. We're talking about proportions.
Theoretical proportion is what is like, we trying to get that then.
We're trying to find we're trying to find, it's not theoretical.
Oh,
That population has a proportion.
yeah,
We just don't know what it is, and we can't find what it is unless we can take a perfectly accurate census. Which for a lot of things, I mean, we've talked about how difficult it is to do a good census,
yeah,
right? You're talking about the bass in Lake Michigan. Remember that one?
yeah.
You're like, or all the fish in Lake Michigan. Yeah, good luck with finding that. Okay? All right. So, do we have time for this?
4 minutes.
No, we're not going to do this one yet. We'll save this one for tomorrow. But again, I want you to kind of think about that idea. If it's a 95% confidence interval, what we believe is once we've found that interval, we believe that 95% of the samples of this size taken from this population will capture the true proportion of the entire population that have whatever this quality is. If you can get your head wrapped around that idea, you're way ahead of a lot of beginning statistics students.
Wait, can you repeat it again?
Yep. If I have a 95% confidence interval, so let's say that I did the M&M and I got 18% and I got this confidence interval, and say my confidence interval is from 16.1% to, what would that be, 19.9%. Okay? I believe that 95% of the time when I do a sample of the size that I used, that 95% of the time I'm going to capture the true
Between 9
proportion of the entire. I believe that the true population, it won't always be between those two. The actual, for the entire population, the proportion will be somewhere in my interval.
Yes, okay, that makes sense. So somewhere between 16 and 19.
Yeah, 16.1 and whatever it was.
Yeah, that makes sense.
We believe so sometimes when I do a sample, it's going to be outside of that, but not very often.
Yeah, that makes sense.
Okay?
And so that's saying like, is that based off one sample?
It's a single sample.
Okay.
So based on that one sample,
We
that's
pull-
how confident we are.
We put them back and we pull 50 more M&Ms
No,
the proportion?
no.
No?
95% of the time, once we do our interval, the proportion of the population that is green is going to be somewhere between those two numbers. If I did it a second time, I'm going to get a different confidence interval
Oh, okay. So it's just for that one specific sample,
for that one specific sample.
and not specific sample as in like anytime you took 50 a minute, it was like that one group of 50.
Yeah.
Okay.
Yeah. So what's going to happen is, let's say we do this and we get a 98% confidence interval, right? So we're like 98% of the time, if I do this, the proportion for the entire population is going to be somewhere between 98% of the samples that I take would give me an interval that includes the true proportion.
98% of the samples you take will include.
We'll have a confidence interval that includes the proportion of the population.
Okay.
So that's what it means when you're saying you're 98% confident,
I get that.
right? And if you want to be more confident, well, you got to be less precise.
Less precise.
And we'll see that when we start making intervals.
Oh, thank you.
And one of the cool things on the NumWorks is that you can put all the stuff in, and then you can, I'm sorry? Oh, I gave you, that's why there was an extra one. I was like, what the heck, man?
So less precise means, does that mean a smaller sample size or not always?
Typically, yeah, it's because of a smaller sample size.
Okay. So if you get that 98%, that means that
Hang on a minute, Ariel, I'm gonna find the blank one.
that means 98%